Welcome friends to today's session. In this session, I'll be taking you through lattice energy and hydration energy, and also we'll look at how we can use the potential energy diagram to relate between the lattice energy and the hydration energy. In the preceding sessions, we shall also continue to look at different potential energies using different thermochemical equations to determine some enthalpy of changes that we don't know, using the potential energy diagrams, using the Born-Haber cycles, and using thermochemical equations. So we shall be looking at all the three methods, but in this particular session, I'll be taking you through the relationship between the lattice energy and hydration energy, as we also look at some other enthalpy changes. It is very important for us to know these different enthalpy changes which are used in Born-Haber cycles and thermochemistry. And I said when we're looking at all of these, we have these Born-Haber cycles. We also have the potential energy diagrams, potential energy diagrams. Then we can also use another method which you call the use of thermochemical equations. So in this session, we are going to look at the different enthalpy changes. We get to know the definition of each enthalpy change, the symbol used, the typical sign, and then the equation. For us to draw very well the Born-Haber cycles, for us to draw very well the potential energy diagrams, to use the thermochemical equations, we need to be knowing these enthalpy changes. The way we have known our names, then it's how we are supposed to get also these enthalpy changes, understanding each enthalpy change, its definition. To know its definition, you also need to know the equation. And when you're talking about this equation with the correct state symbols, we want the equation with the correct state symbols. So don't just get to know the enthalpy change, enthalpy of formation, and you end there. Get to know the definition. Get to know the equation relating to that enthalpy change. Just keep the watch as we go through the whole of this session. I believe by the end of this session, you'll be able to differentiate between the lattice energy, you'll be able to differentiate between the hydration energy, and you also draw a potential energy diagram which is relating hydration energy and the lattice energy. And then in the next session, we shall be looking at other potential energy diagrams, different worked examples, and also we shall be doing some practice items. In this session, teacher Nyirimbibi Isaac is the one who is still taking us through this thermochemistry, and we are going to be having a series of these sessions looking at each and every topic. Make sure that you click on that subscription button, hit the notification button, such that anytime we release a video like this, you are able to get it as the first person. So keep on pausing as you note down all this. These are the equations, these are the enthalpy changes that you need to know in thermochemistry, and if you know them very well, their definition, you know very well their equations, then the potential energy diagrams, the Born-Haber cycles, using the thermochemical equations, it will be very simple for you. So let's begin on the first one. Let's use this color. Enthalpy of formation. From the word formation, we are saying that this is the energy change when 1 mole. Please keep on noting this. When 1 mole of a compound forms from elements in their standard states. From elements in their standard states. So this is the symbol standard enthalpy of formation, and we are saying it is majorly ectothermic. And what are we saying? We are forming 1 mole. It is 1 mole. Here it is 1. You can see when we are balancing, we are not putting a 2 here to balance the chlorine atoms. No. Instead, we are putting a half here on chlorine because we want 1 mole. So what this 1 mole is very important in our definition because it guides us on the equation we're supposed to write. Then we have enthalpy of atomization. This is the energy change when 1 mole of gaseous atoms forms from an element in its standard state. Now, here they're saying when 1 mole of gaseous atom is formed from the element in its standard state. Like now chlorine. Chlorine exists as a what? A molecule. And we are saying that that energy, which is that energy change when this 1 mole of gaseous atom is formed from the element in its standard state is the one we are calling enthalpy of atomization. We can even talk about enthalpy of atomization of sodium. Sodium exists as a solid. So when it forms sodium gas, now the energy change which is produced when sodium solid changes to sodium gas is what you're calling the enthalpy of atomization. Let's look at the third one. So this is our number 1, this is our number 2. Then number 3, we're saying enthalpy of sublimation. Now in enthalpy of sublimation, we are saying that the energy change when 1 mole of a solid turns into gaseous. So sublimation, as we know that when we're studying about matter, the changes of matter, when a solid changes to gas or gas to solid, we call that one sublimation. So enthalpy of sublimation is the energy change when 1 mole of solid turns into gaseous atom. And we can see an example here. A solid changing to gaseous atom. We can see the enthalpy of sublimation. It looks like same as the one for atomization for sodium. But they are different. Like now chlorine cannot undergo enthalpy of sublimation. Are you seeing that? We cannot get enthalpy of sublimation of chlorine. Why? Chlorine in its state, in its standard state, it is a gas. Yet in sublimation, we are looking at a solid to gaseous atom. Aluminium can undergo sublimation. We have aluminium solid, which is changing to the aluminium gas. So that is enthalpy of sublimation. But you can't have a non-metal undergoing sublimation. Then we have bond dissociation energy. We normally summarize as BED. The bond dissociation, it is BDE, bond dissociation energy. The energy change when 1 mole of covalent bonds is broken in gaseous state. Now, when we talk about covalent bonds, we know a covalent bond is formed in a covalent compound. So, which means we have a compound consisting of only non-metals. So, when we have that energy, when 1 mole, now it is 1 mole of covalent bond is broken. So, it is 1 mole. Now, you can see an example of chlorine is being broken into its gaseous atoms. So that one becomes bond dissociation energy. Then ionization energy. The energy change when 1 mole of electron is removed. We are ionizing. We are removing an electron from gaseous. Now this is very important. From gaseous atoms to form cations. So we are removing electron. We have an example, sodium, which is in gaseous state. When we remove an electron, we have sodium in a gaseous state. Remove 1 electron, it will form sodium. It will form sodium ion, which is also in gaseous state. Now, whenever this happens, we are saying that is what we call the ionization energy. And we are saying now this equation here, the equation here I've put, and this one, they are all the same. The difference is that instead of this first equation putting minus electron, they have put it on the other side. And we know when a negative crosses from left to right, the sign also changes. So that's why we see the other side on the first equation, we are having a electron on the right hand side, then here we have it on the left hand side. That is the difference. Then we can move on to this electron affinity. Now, in electron affinity, we are saying that energy change when 1 mole of electron is added to a gaseous atom to form anions. So we are now adding gaseous atom. We are adding an electron to form what? An anion. An anion is a negatively charged ion. And they are saying that the first ionization energy is negative, while the second first electron affinity is negative exothermic, while the second electron affinity is endothermic, which means it absorbs heat, is therefore positive. Why do we not need to know these signs? Because when you're drawing your potential energy diagrams, you need to know the direction. Because if it is positive and you want it to go into negative, there is something that you need to do. So you need to know whether it is an exothermic reaction or whether it is an endothermic reaction. Let's look at also the lattice enthalpy, and this is what we are looking at today specifically, and also the enthalpy of hydration, and lastly enthalpy of solution. Today we want to focus on these three. Then in our next session we shall be looking at the potential energy diagram, which are relating all these. Are we there? So make sure you're paying much attention as we go through these three potential energy diagram relating the three. So it is very important for us to pay much attention, and we see how they relate to one another. Now here we are saying that energy released when 1 mole of ionic solid forms from gaseous ions. So this involves formation. But you recall we have also that is which involves the breaking. So the one which involves formation from the gaseous ion is negative. While the one which involves breaking into gaseous ions, it is positive. But the typical one we have put for us the negative. But it can also be endothermic. A good thing we are going to go through this in the next slide, and then we see what we are talking about there. So in lattice energy, we are looking at gaseous ions. When these gaseous ions combine to form a solid ionic compound, then that energy change is the lattice energy. But also we can have the sodium chloride solid, which is breaking into these ions, gaseous, plus chlorine ions, which are also in gaseous. So this one will give us a positive. It is endothermic. This one is exothermic. So that is for lattice energy, and we are going to look at it in detail. Then we have enthalpy of hydration. Now, enthalpy of hydration, we are saying it is energy released when 1 mole of gaseous ions becomes hydrated. When you say something is hydrated, it has water. So when you add water to that substance, gaseous ion, then we are saying that one, we're calling it the hydration. That enthalpy is called enthalpy of hydration. And we're saying it is exothermic, and we are giving an example. Sodium, which is a gaseous ion, when it dissolves in water, when you add water to this ion, becomes hydrated, forming aqueous sodium ions. Then we have enthalpy of solution, the energy change when 1 mole of ionic solid, still we are looking at ionic solid, dissolves in water to give infinite dilution. When it gives infinite, until when it can no longer dissolve any more solid. That is enthalpy of solution. Ionic solid dissolves in water to give an infinite dilution. We add in more and more solvent. So we are saying that enthalpy of solution can be positive or negative depending, and we are going to explain this more. We are going to put this into detail. When does it become positive? When does it become negative? So I was giving an example: sodium chloride solid. When you add into water, we form sodium aqueous and chlorine aqueous. So that is enthalpy of solution. Then finally, enthalpy of combustion. Energy released when 1 mole of substance is completely burned in. Now, it is 1 mole of a substance that is being burnt in oxygen. So which means this substance that is being burnt, it has to be 1 mole. If you put more than 1 mole, then that's no longer enthalpy of combustion. It changes from enthalpy of combustion. Hope we are moving together. Please, as I said, wait until the end. You don't need to miss out the potential energy diagram relating the lattice energy. Are we there? Lattice enthalpy. We are the one relating hydration energy. That is enthalpy of hydration and enthalpy of solution. And then in our next session, as I said, we shall look at those potential energy diagrams which are rating a number of these enthalpy changes. Please stay on until the end, and we're going to make sure we move faster as we get to know all these things. I'm going to be putting all this work there so that you can even note down and you make your own notes as we go through this work faster. Now, let's look at enthalpy of solution. Now, the enthalpy of solution, we are saying this is the energy change which occurs when 1 mole of a compound is completely dissolved in enough, here they are saying in enough solvent, such that no further heat change occurs. No further heat. That's why the other side we are using the word infinite dilution. So some books they use infinite dilution, but for us we have defined infinite until such that there is no further heat change which occurs on addition of more solvent. So the solution is said to be at infinite dilution. Very good. So we have an example. If you have like sodium chloride solid is dissolved in water aqueous. Yeah, it is here. We form sodium ions and chloride ions. So we are saying that enthalpy of solution depends on 2 energy terms. Okay, that is lattice energy, and also we have hydration energy. And we are saying that enthalpy of solution is equal to the lattice energy plus hydration energy. And the question is, what is lattice energy? Let's look at the lattice energy. So we're saying that lattice energy, which involves bond breaking, is defined as energy absorbed when 1 mole of a solid ionic crystal is broken down into its constituents. So here we have 2 definitions. The one which involves bond breaking, we can see this solid is breaking into its gaseous ions, and we are calling that one lattice energy, which is positive. Then the one which involves bond formation is the energy liberated when 1 mole of a solid ionic lattice is formed from its constituent gaseous ions. So if it is sodium chloride, its constituent gaseous ions will be sodium ion gaseous, chloride ion gaseous, forming this. And we are saying that this one is negative. Why do we need to know all of these? We need to know because if you don't know the definition and equation, from the definition we generate the equation. So we need to know. Now the question is, what are the factors that affect the magnitude? We have seen that a given ionic compound has its lattice energy, and even another ionic compound has its ionic energy. So we are saying the ionic, this lattice energy of different ionic compounds. For example, you find out that sodium chloride has different ionic lattice energy compared to calcium chloride. The lattice energy for sodium chloride is different from the lattice energy of calcium chloride, and the question is why? Why? What brings the difference, and which one is bigger than the other? Between sodium chloride and calcium chloride, which one has a bigger lattice energy? Those are the two things we want to see. And we are seeing that the magnitude of lattice energy, the size of the lattice energy, is depends on the charge and the size of ions. And this can be explained by Coulomb's law. Yeah, we are going to see the Coulomb's law, where we're saying that Coulomb's law says that enthalpy of lattice, the lattice enthalpy of lattice, change in lattice, is directly proportional to Q1, which is the charge on the ions. The first ion, this is the charge on the second ion, Q1 times Q2 over R. R is the distance between the ion center, or it is ionic radius. So when you get the charges, for example, if you have this sodium chloride, it has sodium ions and it had chloride ions, while calcium has calcium ions and chloride ions. So you can see here it has +2 times -1. Here it is +1 times -1. Which one will be having a higher charge? So you can see very well that calcium will be having a higher, because it has a 2 times 1, which is 2. Here it is 1 times 1, which is a 1. So let's see, how does this charge affect? Let's see how it affects. So we are saying, let's bring the whole of this so that we can even be noting down as we go through each one of them. So we are saying that the ionic charge, how does ionic charge affect lattice energy? How does it affect lattice energy? So I'm saying that greater ionic charges, stronger electrostatic attraction, and higher lattice energy. So if the ionic charges are big, then there is a stronger electrostatic attraction and therefore higher lattice energy. How? Let's explain that. So we are saying that the greater the charge on the cation or on the anion, the stronger the electrostatic forces of attraction between oppositely charged ions to separate them. Thus, it requires a greater amount of energy. In simple terms, if we have like calcium, which is 2+, and we have sodium, which is +1. So we're saying that if the charge is higher, are we there? And like on calcium, it has a higher charge compared to sodium. So if it is higher, we are saying that there is a stronger electrostatic force of attraction. This one, the attraction towards the nucleus becomes higher in the one with positive charge compared to the this one with a smaller charge. But which attraction are we talking about? The attraction to attract the other attraction between the opposite charged ions, which means if it is calcium and chloride ion, if this one is having a higher charge, the attraction between calcium and chlorine will be higher compared to sodium and chlorine. Why? Because of the charge here that calcium is having. So they are saying that on the other hand, if the size of charge is on the ion is small, the electrostatic forces of attraction between oppositely charged ions become weaker. They become weaker, and to separate them requires a small amount of energy. So we can see that the ionic size is that's how it affects. If it is big, then we say that there is a stronger electrostatic attraction and therefore higher lattice energy. For example, we have sodium chloride and magnesium chloride. The ions in sodium chloride, we have sodium ions with +1, chloride ion with -1. So then magnesium ion with +2 and oxygen. And how is Coulomb's helping us? Coulomb said that the enthalpy change in lattice is directly proportional to the charge on the first ion, the charge on the second ion over R, where we say that R is the radius. So if it is, which means the higher the charge, are we there? The higher the charge, the higher the lattice. And the smaller the radius, the bigger the lattice. And the bigger the radius, then the smaller the lattice. And now that these are two factors we are looking at, this is the radius and this is the charge. And now, if the charge is big, because it is proportional to lattice, even the lattice becomes big. If the radius is big, of course, since lattice is inversely proportional to radius, it means that because you can see that lattice is inversely proportional to radius. So when this one is big, this one becomes small. If it is small, then this one also becomes big. But for this time round, we are looking at the charge. So here we have +1 times -1, which is -1. Here we have +2 times -2, which is -4. So the magnitude of this is bigger than the other. So this magnesium oxide, that's why it is having a bigger value. 3,000, you see? 3,795. Why this one has only 788? So that difference is due to the charge. Hope that is very clear. The explanation is written there, but we have explained it in detail. Now we have example 2, where we have sodium chloride and magnesium chloride. So the ions are there, sodium ion and chloride ion, then magnesium ion and the 2 chloride ions. So the charges, here we have +1 times -1. This is -1. Here we have +2 times -1. Please, here it is not 2 is not the charge. The charge is this one. So it is -1, which gives us -2. So you can see this is bigger compared to the other one, the magnitude of that. So that's why we see that in magnesium chloride it is 2,489, while here you can see it is smaller. So it is smaller because of the charge. So you're saying magnesium chloride has a greater lattice energy than sodium chloride because the greater charge of magnesium ion, which strongly attracts the 2 chloride ions. Then we have this practice item. Please, this one, practice it, and then you put your response in the comment section. You put your comment. They're saying, explain the observation, the difference in the lattice energy of the following compounds. So we have two compounds, that is calcium oxide, and then we have calcium chloride. Now, calcium oxide has negative 3401, while calcium chloride, it is having 2271. Which one has a bigger value? We can see that this one is 2000, this is 3000, which means calcium oxide has a bigger lattice. Now the question is, why? Why is it having a bigger lattice? Why is calcium oxide having a bigger lattice than calcium chloride? Let me find your responses in the comment section. And also, as a way to know that you guys, you're following what we are discussing. Now, your feedback helps me to know that actually we are moving together. Let's also go to another factor, that is ionic radius. Now, in ionic radius, we are saying that the smaller the ions, then the ions pack closer together. Then we're saying if the ions are small, the more the ions pack closer together, and then the stronger the attraction and higher the lattice. You recall in Coulomb's law, where we say that the enthalpy of lattice is inversely proportional to the radius. This is the radius of the ion. So what does it mean? It means that if the radius is small, then the lattice becomes bigger. And if it is big, the lattice becomes small. So that's why we're saying that if the ions are the smaller the ions, the more the ions pack closer together, and then the stronger attractions. And finally, we have a higher lattice energy. Example, we're having lithium fluoride, which has a higher lattice than cesium fluoride. Why? It's because lithium is smaller than cesium. I think all these are group 1 elements, but lithium comes first and it is smaller than cesium. So that's why we see the lattice energy for cesium fluoride is that the one for cesium fluoride will be smaller compared to the one for lithium fluoride. So we are saying in general that the smaller the ionic size, the shorter the distance between two oppositely charged ions, okay, and stronger electrostatic forces of attraction between the ions. Therefore, to separate ions requires greater amount of lattice energy. So that's why it becomes bigger. And on the other hand, the bigger the ionic size, the greater the distance between oppositely charged ions, and the weaker the electrostatic forces of attraction between the ions, and this reduces, are we there? The magnitude of lattice energy. This reduces the magnitude of lattice energy. Now, let's look at this. Let's compare. Consider these halides of sodium. We are using only sodium and we are looking at the halides of sodium. So we are seeing the sodium fluoride, we have sodium chloride, we have sodium bromide, and sodium iodide. So the ionic radius here, ionic radius increases down the group. You recall, we are looking at ionic radius of what? Of these halides, the halides. Because for sodium is the same size. So the difference is on these anions. Are we there? Fluorine, chlorine, boron, and iodine. Iodine is bigger than bromine, bromine bigger than chlorine, chlorine bigger than fluorine. So ionic radius increases down the group. While the lattice energy, what happens to the lattice energy? Even the lattice energy is decreasing because we say the bigger the ionic size, the greater the electrostatic force of attraction, and thus they require much energy. So we are saying, since this one is having smaller ionic radius, therefore it has a bigger lattice. You can see. While this one for sodium iodide, which is bigger, having ionic radius which is bigger, then you can see that its lattice becomes small. So the lattice energy decreases down the group. Okay, what are the uses? Why are we taking time to study about lattice energy? Lattice energy is important in explaining the stability. Is very important in explaining the stability of ionic compounds. We can have two different compounds. For example, calcium oxide. They give you magnesium oxide, and then they ask you calculate their lattice energy, and then after they ask you tell us which one is more stable between the two. How do you know which one is stable? We can know the one which is stable by using lattice energy. How? We are saying that a large or a more negative lattice energy means stronger ionic bonding. You recall, when the lattice energy and something needs much energy to break, are we there? There is that strong electrostatic force of attraction needed in between the ions, meaning those ones are more stable. They need much energy to break. So we're saying the higher the lattice energy, the stronger the ionic bonding, and therefore the greater the stability. For example, magnesium oxide is very stable due to its very high lattice energy. So when you look at the lattice energy, we can get to know which one is more stable than the other. Then it helps in comparing the solubility. Did you know that you can know which salt is soluble and which one is not soluble? So the solubility depends on the balance between lattice energy and hydration energy. Because we said right away from the beginning that enthalpy of solution is equal to the lattice energy plus hydration energy. So a salt dissolves if hydration energy compensates for lattice energy. What does it mean? If the hydration energy is higher, you recall, if it becomes higher than the lattice, then it will dissolve. If not, it will not dissolve. That's why we are saying that, like sodium chloride dissolves easily. Why does it dissolve easily? Because the hydration energy is approximately equal to lattice. So we are saying that when it compensates, it is not, this one is not higher than this, and this is not very high than the other. So we are saying that difference is a little bit is small or approximately equal. Then we say it can easily dissolve. But like in barium sulfate, which is sparingly soluble, lattice energy is too high. So when lattice energy is too high, that's why you find that this substance, it is very stable. It has a stronger electrostatic force of attraction, and therefore breaking its bond becomes very difficult. Thus, it needs more energy to break it, and therefore it is not very soluble compared to the other one, which has hydration energy, which compensates the lattice energy. Then the last two, it helps in predicting melting point. But of course, from these 2 points, if something is more stable, it will require even more energy, and therefore even the melting point becomes high. So that's why we are saying that the higher the lattice energy, the higher the melting point and boiling point. The lower the lattice energy, the lower the melting points. Then it also helps to explain the decomposition reaction. Decomposition reaction, that some salts like carbonates, nitrates decompose more readily if their lattice, if they have lower lattice energies. For example, sodium carbonate is stable, but silver carbonate decomposes easily due to low lattice energy. Due to low lattice energy. So that is the one we have seen. So the lower lattice energy, the more readily it will decompose. And we have given an example of sodium carbonate, which is stable, and silver carbonate, which decomposes easily due to its law. So this one is very stable, so it will decompose, that its decomposition becomes not very easy. So it can help to explain why some substances decompose easily and while others do not decompose easily. It's due to the lattice energy that they are having. Let's look at this. So when you look at this, we want to look at the last one, differentiating ionic from covalent compounds. So even lattice energy can help to explain to tell us the difference between the ionic and covariant compound, and they're saying the difference between experimental and theoretical lattice energies indicates the degree of covalent character. So if experimental enthalpy of lattice is much higher than theoretical, the compound has significant covalent bonding. So it can help in explaining differentiating between ionic and covariant compound. Now let's also look at hydration energy. You recall in this session we want to look at hydration energy and lattice energy in detail, and therefore we also draw the potential energy diagrams for these two. But we're going to move faster. So what are we saying about hydration energy? We're saying this is the energy liberated when 1 mole of gaseous ions is completely dissolved in enough solvent and that it becomes completely hydrated. So here we're looking at a gaseous ion dissolving in water, a solvent, to form now these ions, aqueous. So here we are moving from gaseous ion to aqueous ions. That is hydration, and they're saying typically it's always a negative. So factors affecting hydration energy. We are saying we have only two majorly which affect. The hydration energy depends mainly on the ion dipole interactions between the ions and water molecules. Let's see. Number one factor is charge of the ion. So the higher the charge on the ion, the stronger the attraction between the ion and partially charged water molecules. This means higher hydration energy. So if you have understood for lattice, then these two cannot be very hard for us, because we know that if the charge is high, then there is a stronger attraction between the ions. And this time round we have the ions for the metal, for the gaseous ions, and also the ones for water, because majorly in hydration we are dissolving the gaseous ion in water so that it becomes hydrated, so, or what you call solvated. So we are saying if we have aluminium ion, it has a higher hydration energy compared to magnesium, and magnesium higher than sodium. Then the size of or radius of the ion, the smaller the ions, the higher the charge density. Therefore, they attract water molecules more strongly, releasing more energy during hydration. So we are saying that lithium, it has a small radius, therefore it has a higher hydration energy compared to sodium ions and compared to potassium ions. You can see for these ones they have the same charge. So the difference is not about the charge now, but the difference is about the size. So lithium being smaller than sodium, then you find out that the attraction becomes higher, and therefore to break they will require much energy. So that's why we can see that it is being affected in that manner. Let's look at these key points. They're saying that if the size of the ion is big, the distance between central ion and water molecules will be low, weakening the attractive forces between the ion and water molecules. Hence, a small value of hydration energy. I believe they have tried to explain it very well there. That if the size of the ion is big, the distance between the central ion and water molecule will be low, weakening attractive forces between the ion. So when the ionic compound, number 2, when the ionic compound is dissolved in a certain volume of water, the overall enthalpy change depends on the lattice and hydration energy. And the sign of the overall enthalpy change depends on which energy factor outweighs the other. Which one is higher than the other? So if we are having lattice plus hydration, and lattice overweighs the hydration, then the overall sign will be for lattice. If hydration is higher than lattice, the overall sign for enthalpy of solution will be for that of hydration, because we say that enthalpy of solution is equal to the one for lattice plus the one for hydration. So if this outweighs, we say that this is negatively charged. Then lattice can be negative or positive. So in this case, it is positive. So if the lattice becomes higher than hydration, overall charge will be positive. If the hydration becomes higher than lattice, overall change will be negative. And what are we saying? That if the lattice energy outweighs the hydration energy, then the enthalpy solution will be positive, and I believe that is clear. And the salt will not easily dissolve at that particular temperature. So if the overall change is positive, that substance will not dissolve. However, if the enthalpy of hydration outweighs the lattice, the enthalpy of solution will be what? Negative. It will be negative, and the salt will dissolve easily in water at that particular temperature. So I believe at that point we have gone through hydration and lattice energy very well, and this is the time for us to practice. This is our practice item that we are going to do, and then we shall be able to do more other practice items in our next session. Make sure you don't miss out the next session. The next session we shall look at potential energy diagram relating all those enthalpy changes that we talked about up there at the beginning of this session. So make sure you don't miss out, and if you have not yet subscribed, it is your time now. Click on the notification button, subscribe, and also don't forget to always share with your friends, because we said sharing is a key. If you don't share, that is very bad, because you're also getting whatever you're getting because of sharing. So share what you have with a friend, and they also keep on benefiting from whatever we discuss. Let's go through this practice item, and at the end, we shall be able to do more practice items in the next session. Here they're saying the lattice and hydration energies of salt AX and BX are given in the table below. Salt AX, BX. Lattice energy positive 880. Lattice energy here 790. Then hydration energy here we have for AX negative 860, and here we have 800. So they're saying construct potential energy diagrams. They're saying potential energy diagram to show relationship between lattice energy, hydration energy, and enthalpy of solution from the data given in the table. So we are going to have two diagrams. We're going to have two diagrams. One is going to be showing. It is going to be showing the one for salt AX, and then the other one will be showing the one for salt Bx. So we have the potential, let's say the potential energy diagram for salt Ax. Then you have potential energy diagram for Bx. Pay much attention, because this is our beginning of constructing potential energy diagram. And also in our next session we shall look at Bonn-Haber cycles, potential energy diagram, and using the other method of cancellation method. All the three methods, we shall be using them in our next session. In this session I've been introducing all of this work, and the next session this work is very important. That's why I said don't miss out our next session. Okay, now for you to pass very well these things, you must be knowing how to write these equations. So when they talk about lattice energy, and here it is positive, what does it mean? If it becomes positive, it means that it involves the breaking. So which means in that case it is Ax, which is a solid, breaking into its ions, and these ions, they are gaseous, X minus. So if it is for B, it is Bx solid, which is breaking into its ion, positive gas, and then X, which is negative. Then for hydration, we say that it is the gaseous ion which is dissolving in water. Are we saying that? That it is completely what? Solvated. So which means in this case we'll be having the ions, these ions, gaseous ions of this salt Ax, the gaseous ions, and they will be dissolved in water. This is aqueous, to form the ions. They are completely ionized, that is solvated, that is negative, and then this is aqueous. So the same case, the ions for B plus gaseous ion plus X minus gaseous ion, giving us the B gaseous aqueous. Now it is being completely solvated, so this is aqueous. Now let's see. So our potential diagrams, we say that these potential diagrams we're going to draw here just something good. So we have this potential diagram here. You can have something here, and this is potential energy in kilojoule per mole, and then we also have the reaction. This is the reaction path. So we have this potential energy diagram, and where are we starting from? Where we are starting from, we can see this is our point 0. So where are we starting from? We are starting from, if this is Ax, we are starting from our salt Ax solid, which is breaking into gaseous ions. It is breaking into gaseous ions, and we are saying that this energy is what? This energy is positive 880. Why did I move up? Because it is positive. If it was negative, I could be moving down. So at this point is where we are forming the A gaseous ions plus X, which are also in gaseous. These are also gaseous ions. Okay, that is 880, but that is lattice. This is lattice energy, which is 880. Now from there we are having, when these ones react, the ions are dissolved in water. Now for them it is becoming 800. It is 800 860. Where do we find 860? This, and it is the negative side, so we are going to move negative side and we move 800 what? 60. So from here to here is negative 880. Are we there? But we are looking for 860. 860, oh sorry, it can't move up to this side. Okay, sorry about that. So we had our line here. Our line was here. So if this is 880, which means when we subtract 860, it will be reaching somewhere here where there is 20. If this is 20, so it will reach up to there. And at this point is where we are forming our aqueous ions. This is X aqueous ions. So this is the enthalpy of hydration, which is negative 860. So the enthalpy of solution, it is when we get this solid and we add it into water, aqueous, we form the, and when we add that, we are able to get this value, and this is the enthalpy of solution. So how do we get the enthalpy of solution? Enthalpy of solution is this distance from here up to here, because we are getting this solid, add it in water to form these aqueous ions, and therefore you can see our answer becomes positive 20 kilojoule per mole. Have you seen that? So we do also the same for this diagram for Bx. So we do the same for Bx. I want to be sure that that is where we want it, and then we also have this line. So we said this is the potential energy in kilojoule per mole. This is the reaction path. Where are we starting from? Now I believe we know we are starting from our Bx solid, which is breaking. It is breaking into its ions, gaseous ions, and that is the lattice energy. It is positive, which is positive 790, and here we are having B positive gaseous plus X minus gaseous, and we said this is for lattice. Lattice, we said you can symbolize it U, and it is positive 790. Positive 790. Maybe let's clear this. Okay. So we are saying lattice is positive 790. Then from there, these gaseous ions, when we add in water, they become solvated. That's when we get the hydration energy. And hydration energy is 800. Yet up to from here up to this line, it is 790. So which means we need to move a little bit down, and we reach up to that stage where we have negative 10. When we move down, 790 plus 10, it becomes what? This is the hydration, enthalpy of hydration, which is negative 80, 100. So this distance from here to here is 80, 100. And here we form our B plus aqueous plus our X aqueous. So for us to get for solution, it is this solid plus aqueous, and then this gives us the enthalpy of solution. So you can see the enthalpy of solution here is negative 10 kilojoule per mole. Very good. You can see we have been able to determine, we have already answered part 2, which was saying determine the enthalpy of solution of each salt. We have determined the enthalpy of solution. It is positive 20 for AX and negative 10 for this other, which is BX. And which of the salts is soluble in water? We said the one which is having Now you see this, the one which is having positive, we say it will not dissolve because the lattice is higher. While the one which is negative, it will dissolve because the hydration energy is lower and can easily dissolve. We can have seen that that is the importance of lattice energy. I want to invite you for our second session in looking at potential energy diagrams, von Haber cycles, and use of thermochemical equation. Don't miss out our next session. Just keep on the look on our channel. Don't forget, it's been Isaac Nyirimbibi taking you through this session. Have a blessed time. Let's meet in our next session. Don't forget to subscribe, like, and share with friends for more tutorials. Have a blessed time. God bless.